Yes.
Okay, good afternoon, and welcome back. We are starting the second course of the summer school, and this is about using gravitational wave observations to probe the early universe. And I'm very pleased to welcome Professor Chiara Caprini, who is at University of Geneva, as well as at CERN in Geneva. She is a theoretical cosmologist, one of the leading experts in early universe cosmology. And she has worked on different aspects of early universe, particle physics, and using gravitational wave observations to probe the early universe. She's also playing a very active and leading role in the LISA consortium. It would have been, of course, nicer if she could come on in person, but I'm very glad and very grateful that among her very tight schedule, she was able to accommodate our kind request and is willing to give this excellent set of lectures. Thank you very much, and please take it away.
Okay, thank you very much for the invitation to give this set of lectures. I hope they'll be satisfactory. Yes, so we will talk about gravitational waves from the early universe. And the first important point to say when we talk about this topic is why gravitational waves are actually interesting to probe the early universe. And the reason is simple, it is connected to the weakness of the gravitational interaction. And this implies that the universe is transparent to gravitational waves. What does it mean? That if you compare some sort of interaction rate of gravitational waves that one can approximate assuming a weak interaction, so decoupling factor squared and behaving like t to the 5, and you compare this with the Hubble rate in the early universe, which for a radiation-dominated universe goes at t squared over mass Planck. What you find is that this ratio is proportional to t over mass Planck to the cube. And therefore, it means that for every temperature or energy scale in the early universe, which is smaller than the Planck scale, which means basically the entire time of the evolution of the universe, basically the rate of interaction of gravitational waves is much smaller than the Hubble rate. Okay, and this means that they are basically decoupled. If you do the same calculation for photons, as you know, you find that with an interaction which is a proton plus electron forms an hydrogen atom plus a photon, you find that this reaction freezes out at about the electron volt. And it is when one forms the cosmic microwave background. If you do the same calculation for neutrinos, you find that this particular weak interaction for the neutrinos freezes out at about 1 MeV. So you see, we do have examples of particles that at some point are decoupled from the rest of the universe because the typical interaction rate gets smaller than the Hubble rate. And for, let's say, gravitons or gravitational waves, this really happens extremely early. And it's all due to this particular coupling. Okay, so what does it mean? It doesn't mean that one cannot produce gravitational waves in the universe. One can, of course, as strong valiant processes, as we will see, that do produce a gravitational wave signal in the universe. However, this simply means that once the signal is produced, it propagates practically without interacting. And therefore, what does it mean now if we focus on the early universe, that gravitational waves, I mean, if we are able to measure the gravitational wave signal from some process in the early universe, they can bring, actually, we can access directly information about the process that generated them. And so there is a clear analogy with the cosmic microwave background because you see, by observing the cosmic microwave background today, we have direct information of what happened at recombination when the universe was 370,000 years old. And exactly the same can happen, at least in principle, with a gravitational wave background generated in the early universe. It would form a fossil radiation, pretty much like the cosmic microwave background, and therefore, if we are able to detect it, it brings direct information about the generation process, and therefore about the status of the universe at the energy at which this particular process was, this particular process of gravitational wave generation was operating. And therefore, this directly translates into a test of phenomena occurring at very high energy, much higher than the cosmic microwave background, as we will see. So this is really where the interest of gravitational waves to probe the early universe stands. Now, there is also the possibility to use gravitational waves to probe the late universe. We won't cover that in my lectures, but I believe you have lectures about this, and in that case, one uses the signal from compact binaries that orbit around each other and possibly merge and emit the gravitational waves, and therefore these also, if we are able to catch these gravitational waves, which is what has happened with the Earth-based interferometers, they also bring direct information on the source, which in that case is a binary. And we can use then this signal also to do cosmology and test the late universe. But so in this course, we will really focusing on the early universe. And so there are basically two parts. The first part is really about definition of gravitational waves, their energy momentum tensor, how we can actually formulate them in the Friedmann-Lemaitre-Robinson-Walker spacetime, which is the one that describes our universe, so a spacetime in expansion. We will see what is the gravitational wave equation of motion in this space-time, and we will give some relevant solutions. And this is probably the subject of today. We'll see how far we go. And then in the second part of the lectures, instead, we will focus on characterizing, first detecting and then characterizing the gravitational wave signals from the early universe. We will see why they are actually stochastic in nature. So what does it mean to talk about a stochastic gravitational wave background? And we will see the potential of, so first of all, what is already known about this signal, and what is the potential of several observatories, present and future, to access this kind of stochastic signal from the early universe. And I will spend a bit of time detailing the measurement by pulsar timing arrays, which, as I'm sure you know, is most probably the first ever measurement of a stochastic gravitational wave background, which is most probably not of primordial origin, so it hasn't been formed in the early universe, but one never knows, the possibility is not excluded. In any case, so I will try to detail how these pulsar timing arrays can be used to measure gravitational waves. And then in the last part of the lectures, I will provide a few examples of stochastic gravitational wave backgrounds from the early universe, trying to detail the possible emission processes and the characteristics of each signal depending on the emission process. The material for these lectures is based on a review that we wrote together with Daniel Figueroa, and you can find here the reference, especially the first part of the lectures. You can find the material here in this review. And also, what is very important in this topic is to read the book by Professor Maggiore, called Gravitational Waves. There are 2 volumes about this, and in particular the first volume is important, and all the first part also of these lectures is taken from this particular book. And in volume 2, what is important is especially the pulsar timing array part. Okay, so I encourage you to have a look at these references. Okay, so now let's start with the first part, which is pretty introductory. So what are gravitational waves? I'm sure you all know, but let's repeat it for clarity. So it's important to remark that gravitational waves emerge naturally in general relativity. Why? Because general relativity is a theory that has been formulated because of the necessity to build a causal theory of gravitation. And so a causal theory like special relativity or electromagnetism, right? Because Newtonian theory does not have this causality property. So when you combine actually, or when Einstein combined the properties of Newtonian theory that actually describes very well the solar system, so it is a good theory given some boundaries. But when Einstein combined it with the concepts of causality that emerges in special relativity, then of course he found out that there must be some form of radiation in this new theory that propagates the information causally. And these are precisely gravitational waves. Okay, so that's why they actually emerge naturally. So in reality, if one look historically, it has been extremely difficult to find these wave solutions and to convince all the community that these waves are real and exist. Why? Because of gauge issues. So people, obviously one finds propagation modes, but they are, one needs to fully resolve the gauge dependence before one can access the real physical degrees of freedom of these waves. And this is quite an involved process that we will try to sketch. Okay, so what in general, waves in physics are propagating perturbations over a background, right? That carry out the characteristics of the perturbation. So in general relativity, the procedure is the following. One needs to then take a background space-time metric, okay, and which is in the theory the gravitational field, right? So what was like in Newtonian theory, the gravitational field is promoted in gravitation in general relativity to really being the characteristic of the space-time, so it becomes the space-time metric. Okay, so this one needs to choose a background space-time metric that then one needs to perturb with a small perturbation over this background metric. And then as you do in classical mechanics, right, you want to solve the equation of motion of the theory for this small perturbation. So you insert the perturbed metric into Einstein equations, so the equation that describe the space-time dynamics. And then, if everything goes well, one then finds a dynamical solution for the perturbation, which is propagating as a wave. Okay, so this is the procedure to actually express the fact that the theory does contain a wave-like solution and therefore gravitational waves. So the first clear question that arises here is which background metric to choose for this. And of course, the simplest choice is to choose flat space-time. Right, it is a perfectly fine solution of general relativity when it's a vacuum solution, flat space-time. So let's go ahead with that as a first definition of gravitational waves. So so the fact of choosing Minkowski metric, so flat space-time, as a background solution leads to the linearized theory over Minkowski, and this is the simplest case in which one sees the appearance of gravitational waves. Okay, so let's go ahead. We have then a general metric that we write as Minkowski plus a small perturbation. Small meaning really that its amplitude is much smaller than 1. So thanks to this condition, one can linearize all objects of this theory at first order in the h mu nu. So a first order in the perturbation, which in particular means that whenever possible or whenever necessary, one can raise and lower indices with the background metric eta mu nu. Okay, so the first thing one wants, of course, to formulate in the case of this linearized theory is the affine connection, the gammas. And it is very easy to demonstrate that the affine connection takes this form. So you see here in principle, as you know, the gammas are quadratic in G mu nu. Okay, and in particular are given by products of G mu nu and its derivative with respect to the coordinates. But when you actually apply the linearization at first order in H mu nu, this is the only component that does not vanish, and it is not at second order in H mu nu. So, for example, just to tell you one term in which there is eta mu nu, right, that just raises and lowers the indices, and then the derivative of eta mu nu would be 0. So everything that is a 0th order goes away, and everything that is a second order, you throw it away, and so what you are left with is just the derivative of h. This you can calculate if you want to derive this expression. The Riemann tensor is a bit more involved, of course, to derive, but in the end, it also takes a very simplified form in this linearized theory. And what is also important to notice here, and you can find this in the book of Michele, or also the book by Strauman, is the fact that the Riemann tensor in linearized theory is actually invariant under coordinate transformation, rather than being covariant as it is in the general theory. And this is something that is used in the definition of in the analysis, for example, of a detector, how it detects gravitational waves. But we won't do this, we won't consider this in this course. Okay, and then the last thing one wants to obviously to write down is the Einstein tensor, which is possible to write it down once you have the Riemann tensor. And the reason why one needs the Einstein tensor is because, as I said before, we want to insert right, this quantity into Einstein equation to see what is the dynamics of this perturbation. Okay, so here box means simply the derivatives with respect to this, with respect to the coordinate in Minkowski metric. Okay, so there is every time here one would have an Fi connection coming about, it is zero, obviously, because this for this part it is zero, for this part one throws it away because it always gives terms at second order. Okay, so box is simply this, as you are used to in electromagnetism, and this little bar here denotes not exactly the initial metric perturbation, but a transformation of it that is useful because with respect to this bar h mu nu, the Einstein tensor, it takes this simple form, and this is what is called the trace reversed metric perturbation. So you simply take the original one and you subtract 1/2 of its trace. And this H bar, you see, it is possible to use it because we remain in the same theory. It is still small, right? It still satisfy this condition. Okay. Now that one has the Einstein tensor, one can actually remark that there is indeed a term which very much looks like the operator of a wave equation, and it is this term box h bar mu nu. So considering the fact that the Einstein equations are simply g mu nu equal 8 pi g times t mu nu, where this is the energy momentum tensor, and so it is the source of the metric perturbation, right? One sees that, but if I have this term, then I would resort here to a wave equation, provided that all the other terms are zero. So all the other terms have a very similar form, which is d mu h bar mu nu equals zero. So one would like to see whether it is possible to set this condition. Now, the answer is yes, but what do you need to do to choose this particular condition without imposing any restriction on the theory? Well, the fact is that general relativity is invariant under general coordinate transformation, right? So every physical quantity can be expressed obviously using a coordinate transformation or picking an observer or a frame as you like it. But when you perform a coordinate transformation, so you change the frame, you change the observer, the physics must remain invariant. Okay, this is a general condition, and particularly it is true, I mean, for many theories, but also in general relativity. So this is the basic properties of general relativity. What happens here, we are not dealing exactly with general relativity, we are dealing with this linearized theory over Minkowski. And it turns out that the linearized theory over Minkowski is invariant under coordinate transformations that have a particular characteristic, which means that they are infinitesimal or slowly varying. Okay, let's try to see why. We suppose that we perform a coordinate transformation that brings your original coordinate system into a new coordinate system x prime, where I have translated the initial coordinate system by some quantity, by a 4-vector. Okay, so you already see this is a particular kind of coordinate transformation, is not a general one. Okay, so let's apply this, and therefore one can study how the original metric will transform into a new primed metric as a function of x prime, so this new coordinate system, and the transformation, you can verify it in the exercises, is particularly simple because once again, one always linearizes in h mu nu. And in the end, this is what you find. Okay, and so this is the new metric, and now the thing one wants to obviously verify is this new metric still okay in the context of this linearized theory? So does it satisfy as well the condition to be much smaller than 1? Well, this is only true if your coordinate transformation satisfies this condition. Okay, so you know that h mu nu is already small. You are now changing it by this transformation. So if this particular term is of the same order or smaller than h mu nu, then it is guaranteed that you remain in the linearized theory. Okay, so this is what it means that the linearized theory is invariant under slowly varying coordinate transformation. You see, this is a derivative with respect to space and time, and so we want this derivative to be small. Okay, and now let's study. So I remind you that we wanted to perform a coordinate transformation to be able to set this to 0, okay, to be able to see whether we can actually write Einstein equation as a wave equation. So we need to study how this particular term transforms. Okay, and this is also something you can do in the exercises, and it is easy to show that it transforms with the box psi mu. Okay, so the derivative with respect to the coordinates in this new coordinate frame of the new metric perturbation is the derivative of the old one minus box psi mu nu. Now, the point is that you would like then to go to a coordinate system in which this guy here is equal to 0, right? So that you can write Einstein equation as a wave equation. And is that possible? The answer is yes, because it is always possible to solve an equation like box psi equals something. Okay, there is a green function that is well defined that you can assign and to solve for psi mu nu. Okay, so it is always possible to find a 4-vector psi mu nu such that here you actually go to the new frame x prime in which this is satisfied. Okay, and this is called the Lorentz gauge. Okay, so one does this kind of transformation, chooses this new gauge in which the physics is exactly the same, okay, and in this new gauge there is this condition that is satisfied. And therefore, now I've dropped the primes, etc. And therefore, in this particular Lorentz gauge, all the terms in the Einstein tensor that contained a derivative of h bar now prime go away, and Einstein equations take the form of a wave equation. where T mu nu is the energy momentum tensor of the source of the metric perturbation. Now, what is also nice to observe is that from the Lorentz gauge condition, which is this one gets d mu T mu nu equals 0. So this is familiar, I'm sure, with you, because this is what in flat space-time represents the conservation of energy and momentum. And so the fact that in this linearized theory we find this means that the energy momentum tensor of the source is indeed conserved. So this to first sight is very nice. You say, okay, everything makes sense. I recover energy momentum conservation, perfect. On the other hand, in this kind of linearized theory, this has a very specific meaning, because it means that the source, so we are not there yet, but when we will be able to ascribe this metric perturbation to gravitational waves, this is going to be the source of the gravitational waves. And so this particularly means that the source does not lose energy and momentum by gravitational wave emission. Okay, and this is not something you would like, because of course, a binary source, for example, that produces gravitational waves must lose energy and momentum that are carried away by the gravitational waves. But this means simply that in this linearized theory over Minkowski, the background space-time, as we already said, is Minkowski, so it's flat, and therefore the source, this T mu nu, the source of gravitational waves, is described by Newtonian gravity. Right, and so and therefore basically the outcome is, and it is correct in the context of this theory, is that this theory does not describe how gravitational wave emission influences the source. Okay, the source is simply, for example, a binary a binary of compact masses in Newtonian gravity. So it simply go on in spiraling. It simply go on circulating one mass around the other without losing any energy by the emission of gravitational waves. So then in the context of linearized theory, you can have a look, because this I won't cover here, is done, I suppose, in the lectures about the binary emission, but you can see it in Maggiore's book. It is possible to remain in linearized theory and analyze the emission of gravitational waves. This leads to the what is known as the chirp solution for the gravitational waves. I suppose you probably know it already. But you need to perform a trick to do that. Okay, so you can look this in Michele's book. But what we will see in the context of this theory is that it does not describe how gravitational wave emission influences the source, but it can be used in all generality to describe the behavior of test masses. Okay, because by definition test masses are test, and so they do not back react on the space-time metric, and therefore one can actually use this theory to describe the test masses. Okay, so this was a bit of a deviation just to clarify the meaning of this particular relation in linearized theory. Okay, now let us count degrees of freedom here in this new frame that we have chosen, the Lorentz gauge. So we have started with a symmetric space-time perturbation in 4 space-time dimensions, which then has 10 degrees of freedom. We have imposed to be in the Lorentz gauge, which means that this has 4 independent conditions. Okay, nu are 4 for indexes from 0 to 3. And therefore, this means that in the context of this theory, in this Lorentz gauge, one has 6 radiative components. And the question is, are these components all physical? So in order to answer this question, one needs to verify whether if you perform another infinitesimal coordinate transformation, you do remain in the same gauge. So it means that you have exhausted the freedom of coordinate transformation. Because otherwise you can still have into this quantity some spurious gauge modes that you don't want, right? Because you want to find only the physical the physical terms of this metric perturbation. So the answer is no, they are not all physical, because there is still residual gauge freedom in the Lorentz gauge. And this can be verified by then performing another coordinate transformation, slowly varying coordinate transformation, that satisfies box psi mu equals 0. Okay, if you choose your psi mu of your new, that defined your new coordinate system that satisfy this condition, you do remain in the Lorentz gauge. Why? Because your metric perturbation in the new frame transforms in this way. Okay, where this tensor psi mu nu is given by this expression. This you can also verify on your own. It's also a simple calculation. And now, of course, you see that the new metric perturbation satisfy these particular remains in the Lorentz gauge, so satisfies again this relation with respect to the new coordinate system if this condition is satisfied. Okay, and that's because if you now apply here a derivative, okay, a derivative of this quantity is 0 if here you get a box, and if the box is 0. Okay, so we have seen that there is still some gauge freedom that we want to get rid of. And now comes the point. In the context of this linearized theory, as we have expressed it now, one can only exploit this residual gauge freedom if one is in vacuum. What does it mean? That we set from now on the energy momentum tensor to be 0. Okay. And if we perform this choice, okay, that we are in vacuum, what you observe, therefore, is that box h bar h mu nu from here becomes equal to 0. Box of this particular tensor is also equal to 0. And therefore, box prime of h mu nu prime, which is the new metric perturbation in this new coordinate system, becomes box of h bar mu nu plus psi mu nu, okay, so it is also 0. So you basically, when you choose to be in vacuum in the Lorentz gauge, you perform this coordinate transformation, you do remain within a vacuum equation. Okay, and this means that then you can use this residual gauge freedom to impose new conditions that your H prime must satisfy. Okay, and so restricting to vacuum space-time, the residual coordinate freedom can be used to fix 4 constraints. Okay, and this amounts to choose what is called the transverse and traceless gauge. Traceless because these four new constraints that one wants to pick are the following. The first is that the trace of the metric perturbation expressed in the new reference frame is zero. And also that it is transverse, which means that all the zero I component of the metric perturbation in this new reference frame are also zero. Okay, and this is called the transverse condition because you remember that the particular metric H prime also always satisfies the Lorentz gauge condition. Okay, so we have chosen this so that we do remain in the Lorentz gauge because we want to exhaust the remaining gauge freedom, okay, remaining in the Lorentz gauge. So this condition is true. So if you now put 0 here in the index mu, you get di hi0 equals 0. Okay, so this condition comes from free. And this is the condition that, as we will see, tells you that your wave, so your metric perturbation, is actually transverse. Okay. And then if you do the same, so you take this condition now and here, wait a second. Yeah, no, sorry. So I got it wrong. So here you had to put J to get this condition. And now you take this one and here you put 0. And so you have D0, H00 plus DI, HI0. Okay, but HI0, you have put them to 0. And so you also find that H00 is non-dynamical. So the time derivative of H00 is 0, and therefore you can actually put, because you know you're looking for a dynamical solution, directly that H prime 00 is 0. Okay, so these two conditions come for free. And the first one is what is called the transverse condition. Okay, so is all that we did, okay. The answer is yes, it is okay, because we have restricted to vacuum, and once we restrict to vacuum, we can actually choose this transverse and traces gauge. And let's see why. So, of course, when you restrict to vacuum, this is Einstein equation, right? It comes from here when T mu nu is 0. This equation implies that box of the trace is also 0. This you can verify, okay, it's a one-line calculation. Box of the trace of H bar in the X frame is 0. Now what happens in the X prime frame, the one we want to transform to, that is meant to be the transverse traces gauge? So this is how the trace of H bar transforms. Okay, so it is easy. It's just the trace of this quantity. Okay, I take the trace here, the trace here. And it means that in the prime reference frame, H bar is H bar minus this. Okay, and now you want that in this prime reference frame, your metric perturbation is traceless. Okay, that's the first condition of the gauge you want to transfer to. But then from this condition, it implies that H bar is 2 d mu psi mu. Okay, and therefore it is fine, because now if you here apply a box, okay, you want to get to 0, because otherwise you have a contradiction. And indeed it is okay, because the very first condition we imposed on this psi mu that define the new coordinate system is that box psi mu is 0. So everything is okay. On the other hand, if we were not in vacuum, okay, the Einstein, applying the trace to the Einstein equations would have, of course, led to this condition, which here you would have that box H bar would not be T mu nu, but would not be, sorry, 0, but the trace of T mu nu. And therefore, this would imply, because this particular transformation would remain the same, and therefore this would imply a contradiction. okay, because you want to choose the new gauge, the new coordinate system in which this guy is 0, but then this implies that box H bar is 0, but then you run into the contradiction if you did not choose to be in vacuum to start with. Okay, so basically this transverse traceless gauge, it appears that it can only be picked in vacuum. Now we remain, it still would remain to demonstrate that we can actually choose these 4 functions psi mu in a way that these conditions are satisfied. This is a bit involved, but is done in the book by Straumann, so I refer you to this book to demonstrate this. And now, basically, what happens is that you take your equation, this one, okay? So in the prime reference system that you have now verified, everything is coherent, and you can apply to H prime mu nu the conditions of being transverse and traceless. Okay, so you can rewrite this equation like this. So, which means that the only non-zero component that are left are H, I, J. Now I'm dropping the prime, okay, for simplicity, but this X here now is the coordinate system of the transverse traceless gauge, and this T, of course, as well. Okay, so we have now simplified the situation to the minimum, okay? And because, as Straumann shows, you can actually freely choose 4 functions, okay, in this new coordinate frame. We were left with 6 radiative components here before doing all this business. Now we subtract 4 free function. I mean, you can, by choosing these 4 free function, you fix 4 conditions, and what you are left with are therefore just 2 physical degrees of freedom. Okay, so there are only 2 remaining physical degrees of freedom in this metric perturbation, and these are the physical polarization state of the gravitational waves. So now we are fine, we have exhausted all the gauge freedom, we are left with this simple equation. We have restricted ourselves to vacuum. And then this equation is easy to solve, right? One can simply write this as a plane wave, okay, with some free coefficients that are determined by the initial conditions, and one can express these 2 remaining physical degrees of freedom as 2 tensors. Okay, and the solution then of these equations are plane waves. Okay, that's what it is here. This is imposed by the box, of course. Plane waves, they are transverse, that's what I explained before. They move at the speed of light, okay? This you can see it from here, the fact that you don't have a k and omega, but k is equal to omega. Okay, so they move at the speed of light, and this is also a condition imposed by the box, right? If you of course all know Maxwell's equation is exactly the same. And they have 2 independent polarization components, the plus and the cross. Okay, so now let's see what it means. Okay, so here in this Fourier decomposition in which we have expressed the wave solution, I have this basis tensors. Okay, and what does it mean? It means that if one fixes the direction of propagation of the wave, k here, it's the direction of propagation of the wave. The wave is transverse, okay, that's this condition, so it means that it lives in the orthogonal space. here, very much like electromagnetic waves, but now these are not vectors like electromagnetic waves, these are tensors. And so in the basis of this space, this plane orthogonal to the direction of propagation, one can define these two tensors. Okay, MIMJ minus NINJ, this is the plus tensor, and the cross is the product, mixed product. And therefore, for a free wave traveling in the z direction, now without loss of generality, we can fix k as being the z direction. This is the solution. Okay, so now I have simply rewritten this exponential just as a cosinus. Okay, omega is actually equal to k. Okay, so I've just rewritten like this. Here you recognize the typical form of a wave, so t minus z. Okay, so of a wave propagating in the z direction. And the components of these waves are actually a 2 by 2 tensor that is traceless, so H plus and minus H plus, you see here. And of course, it needs to be symmetric. This is the condition of a metric that we had to begin with. Okay, it's because H is actually a metric. Okay, and then you can perform this exercise to write the metric line element in this particular coordinate choice, in which, first of all, we are in the Lorentz gauge. Second, we are not only in the Lorentz gauge, but in the transverse traceless gauge. And third, we have decided that the wave propagates in the z direction. And in this case, the metric element is simple. The time part is not affected, okay, remains the one of Minkowski. The z part, of course, is also not affected because I just said that the wave is transverse, okay, so the wave or the metric perturbation leaves orthogonal to k. So this part of the metric element is not modified. And the other parts, the space dx squared, dy squared, and the mixed term are affected by this part of the metric tensor. And so you see, we are in linearized theory, you remember, so this one is the one that comes from Minkowski, okay, plus the small metric perturbation, H plus is this part, minus H plus is this part, and the cross, of course, enters in the dx dy element. Okay, now I hope everything is clear, and one can find in the Misner, Thorne, and Wheeler a book, which is an extremely complete review of general relativity that I strongly advise. That in all generality, the polarization states of a wave are related to the spin of the massless particle that you expect upon quantization of the theory. Okay, this is easy to see, of course, in electromagnetism. It is the easiest example in which this relation can be satisfied, where what is theta? Theta is the rotation angle under which the polarization modes are invariant. So in electromagnetism, this rotation angle, because you have a vector, is actually 2 pi. You have to perform a 2 pi rotation to go back to the same polarization mode, and indeed, when you quantify then the theory, the photon has a spin 1. Okay, so what happens here in gravitational waves? One can ask the question, okay, so if I suppose that everything goes the same way, which is true, then I can find the rotation angle under which the polarization modes are invariant. Okay, and this will tell me what is the spin of the massless particle that I would expect upon quantization of this theory. And let me open a parenthesis. This theory can be perfectly quantized. There's no problem here of, the fact of finding a quantum theory of general relativity is, of course, an open and big question, but in the context of linearized theory, this linearized theory over Minkowski, this can be done without any difficulty. And you do find the graviton, okay, which, as you all know, is a spin 2 particle. And this you can find in Maggiore's book, for example. I'm not doing it here. Okay, but so is that okay? Yes, because if you now we have this simple expression here, okay, so we can say, okay, let's perform a rotation of this around the vector k of an angle theta. What is the angle with which I go back to the same polarization modes? And this you can actually do. You apply a generic rotation around k of this metric by an angle theta, and you find that h plus and h cross, they change in this way. And so if you want to go back to the original h plus and to the original h cross, you need to choose theta equal pi. Okay, and theta equal pi in this particular formula then tells you that the graviton has spin 2. Okay, so we have seen that the fact that gravitational waves have only two independent degrees of freedom, that you can actually express them using this transverse and traceless gauge, which is the gauge in which you have exhausted all the gauge freedom, and so you do access the physical degrees of freedom, is in perfect agreement with the fact that when you expect, with what you expect upon quantization of the theory, which is a particle of spin 2. So everything goes well. And then this particular form here and metric line element, they can be easily used to study the effect of gravitational waves on a ring of test masses. I remind you, as we have said before, that this particular linearized theory can be used to describe the behavior of test masses, okay, that do not perturb the metric by definition. And so this can be done, and I leave this as an exercise. It is not completely trivial, okay, because you need to start from the geodesic deviation equation. And you need to write down the geodesic deviation equation in this, that takes this form, of course, and you need to know what is the Riemann tensor, okay, that I had on my first slide. So then you write the Riemann tensor in the TT gauge, and this is what you find. Okay, so this is also not completely trivial. One needs to calculate a little bit, but what is important, as I said before, is that the Riemann tensor is actually invariant. Okay, so this metric perturbation is the metric perturbation in the TT gauge, but can be also in another gauge. But for us, we leave it in the TT gauge, and actually you then write this displacement vector, exploiting the metric line element, and what you find is that the plus polarization on a ring of test masses, we have now the gravitational wave coming, the z direction is perpendicular to the plane here of the slide, perturbs or deforms a ring of test masses in this way. Okay, so it stretches it in one direction, and then it stretches it, say in the y direction, and then it stretches it in the x direction. And this is, you see, the plus enters in dx squared and dy squared. Okay. While the cross term enters in dx dy, and so using this equation is then easy to show that the effect of the cross polarization on this ring of test masses, you see the displacement here, you need to read this psi I as the displacement of each of these masses, will have a component which is both in x and y direction, and so it will stretch the ring first in this direction and then in this direction. Okay, this is also something that you can do as an exercise if you want, and you can find solved in Maggiore's book, volume 1. Okay. All right, so maybe it's better to have a 5-minute break. I don't know what you think before we go on.
Sure. Would you like take questions now?
Yes, I can. Yes.
Are there any questions on this so far? There's a question. Can you hear me?
Yes.
Yeah. So you showed that there are only two degrees of freedom by going to the transverse and traceless cage, and then you argued that this in fact is manifested in the fact that there are only two spins for a graviton. But I'm just confused. So we chose a particular gauge, and in that gauge we had only 2 degrees of freedom left, which are transverse. Now suppose if I go to a different gauge or a coordinate system in which there's a transverse component to the wave also. So then how does one do this analysis? I mean, first of all, I would like to know whether we have shown that gravitational waves are always transverse in nature, or they're transverse in a given, they can be seen to be transverse in a given gauge.
Okay, so I'm not sure I understand exactly the question, but so what we have shown here is the following. If you want to find the physical degrees of freedom of a physical quantity, or in this case of the gravitational wave, you need to express them in a frame in which you are sure that there are no spurious gauge modes. Okay? And we have demonstrated that if you are in vacuum, this particular frame exists. It is the transverse traceless frame. And in this frame, we have calculated that the gravitational waves have only 2 degrees of freedom. Okay, so it is the fact that the gravitational waves have only 2 physical degrees of freedom is a consequence of all the transformations that we have done, you know, to exhaust completely the coordinate dependence. Now, I have also told you that this is actually connected to the fact that the graviton is a particle of spin 2, which means that our choice or the fact that we could only do so in vacuum is a restrictive condition. We would like to find a general case in which the gravitational waves have only 2 degrees of freedom, and this is what we will do next. So basically, I hope this answers.
Yes. Okay, let me reframe. Are we sure that there is no choice of gauge in which, let's say, the gravitational waves have only one transverse degree of freedom and one longitudinal degrees of freedom? Are we sure that such a
we haven't showed that directly, no.
Okay.
We have chosen, so no. But that sort of coordinate system, I mean, if it is, no, I don't think it can exist, actually. But there can exist, you can perform, you can find, I suppose, a coordinate system in which you do have a longitudinal degree of freedom. Okay, so if you are in the Lorentz gauge and this is your equation, nothing here forbids to have a longitudinal degree of freedom. Okay, but actually you would be fooled because this longitudinal degree of freedom is not physical. It is not a true degrees of freedom, physical degrees of freedom of gravitational waves. So the procedure is just to say, okay, we have found the Lorentz gauge. In the Lorentz gauge, we have this equation. Are all these components that are 6, are all these radiative components physical? And we have demonstrated that the answer is no, because in this particular frame, there are still a residual freedom, and we can choose a frame in which this is transverse and traceless. Okay. And once you have found a frame in which you have exhausted all the freedom, then you are sure that this is the frame in which your quantity is physical.
Okay, yeah, thanks. That helps a lot. Thanks.
Okay, good.
I have a little question regarding the Lorentzian gauge slide. Could you just go? Why do you choose the zeta, the D'Alembert of zeta to be 0? Yeah, the last line is supposed to be obvious. Like I cannot see why D'Alembert prime is approximation to D'Alembert, because zeta there is no condition. I mean, like x mu is zeta mu. That is not supposed to be small.
Yeah. So psi mu nu is this one.
Yeah, but I am asking the last line.
Yeah, exactly. And I am explaining. So psi mu nu is this quantity. Okay,
Sure.
this quantity is small, right?
Oh.
Because we are performing an slowly varying coordinate transformation. Again, these are the only coordinate transformation under which the theory is invariant. So one can only perform this coordinate transformation. So psi mu nu is small. And on top of that, box psi mu nu is 0, because we have chosen it since the beginning, because we want to remain in the Lorentz gauge. So now box prime becomes box, H prime becomes this quantity, and therefore box psi mu nu is 0 by definition. Box H bar mu nu is 0 because we have restricted to vacuum, and therefore box prime H prime is also 0.
Yeah, so why box prime is box? So that's what I am asking. So box prime is
you need to calculate it.
Okay. So
it's not obvious. You see,
sure.
you need to perform this transformation. You need to rewrite the box to linearize everything, and then you find this.
Okay. Thank you.
It's probably done in Maggiore's book. Yes.
Thank you very much.
So I have the same question. I mean, the first gauge transformation you performed was because of the gauge freedom of taking the perturbation, choosing the perturbations. But the second one, where you put a box of xi equal to 0, is because of the coordinate degrees of freedom, right?
It's because you want to remain in the Lorentz gauge.
Is it the gauge invariance of the theory, general relativity, or?
They are both, so you can always perform this kind of, so this is what I explained here. You can always perform this kind of transformation, provided they satisfy this condition, okay? So they are infinitesimal or slowly varying, to remain in the linearized theory, okay? So you are exploiting here two things. First is the fact that general relativity is invariant under general coordinate transformation. Then you want to see which kind of coordinate transformation this particular linearized theory is invariant to, and these are infinitesimal slowly varying coordinate transformation. Okay, that satisfy this and take this form. Now you can actually do this thing how many times you want, right? You can change your frame how many times you want. So first time we do it to go in the Lorentz gauge. And then we say, okay, now we are in the Lorentz gauge. Is there still some residual gauge freedom? So can we perform another transformation of this kind that such that we do remain in the Lorentz gauge, but there is still some choice of coordinate to be made. And the answer is yes, okay, because if you do this coordinate transformation now with the psi mu, it is not the same psi mu as before, because this one satisfies box psi mu equals 0, then you see that you can actually impose new conditions here, but always remaining in the Lorentz gauge, because you have this.
Thank you.
Okay.
So there are some questions online. Would you like to take them now or later?
Maybe we go on a bit, because I have still...
Yes, yes. Why don't, would you like to take a break now or would you like to continue?
So I meant to finish at midday, right?
Sorry?
I am meant to finish at 12.
Yes, in 20 minutes, yes.
In 20 minutes. So I would rather go on.
Sure, please go on, yes.
Okay. And then I will stop maybe 5 minutes before and take the questions.
Sure, sure.
Okay. Okay, now, as I said, what we have done up to now was to find gravitational waves in this linearized theory, but we had to restrict to vacuum, okay? And this was the only possibility in which we could exhibit the two physical degrees of freedom of gravitational waves. And I showed here actually that if we did not restrict to vacuum, then we would have found a contradiction. But of course, this is slightly unsatisfactory, right? Because as I already said, the fact that gravitational waves have only two physical components or degrees of freedom is a manifestation of the intrinsic nature of the gravitational interaction. Okay, that is mediated by the graviton, which is a spin 2 massless field. That massless, meaning that it is transverse, of course, that has only two independent helicity states. Okay, so you see here that we are saying, okay, the fact that gravitational waves have only two degrees of freedom is indeed some kind of intrinsic physical property of the gravitational field, okay, of the theory. So it is a bit unsatisfactory that we could only show this by restricting to vacuum. This should be true also in space-time with matter. And indeed, it is true, right? Also in space-time with matter. But one cannot, in order to do it, one needs to, in order to find that it is true also in space-time with matter, one needs to do things a bit differently. Okay, so all the first part is correct. It's fully correct within its premises. Okay, but here I want to show you that this property of gravitational waves, that they have only two propagated degrees of freedom, is actually more general, and we can indeed find a radiative metric perturbation with two physical degrees of freedom, also where we don't, when we don't impose that T mu nu is equal to 0. Okay. So we need to drop the condition of being in vacuum. Okay, and how do we do it? Then we start from a different situation in the sense that instead of doing all these gauge transformations like this, we exploit the fact that Minkowski spacetime is invariant under spatial rotations. Okay, and we split the metric perturbation into irreducible components under rotation, scalar, vector, and tensor. Then out of these components that are irreducible under rotation, one then construct new metric perturbation variables that are invariant under infinitesimal coordinate transformation. Okay, so we do the same thing as before. We exploit the gauge, the coordinate freedom in order to get rid of all the gauge invariance. And we find variables that are actually invariant under coordinate transformation. Okay. So these quantities are now invariant in general. Okay, so whatever coordinate frame you choose, these quantities are the same. So these are the physical quantities. Okay, and we find then that the metric perturbation variable that obeys a wave equation is indeed the one that have 2 degrees of freedom. And so we are able to define gravitational waves without restricting to vacuum. Okay, so this is the general path. Now let's try to see it, how to do it. Okay, so I said we need to exploit the invariance of Minkowski spacetime under spatial rotations and split the metric perturbation h mu nu, which is still, we are still in linearized theory over Minkowski, into irreducible components under rotations. Okay, so this is, we have seen 4x4 symmetric tensor. And once we, so its components that are irreducible under rotations are these, where now there are 4 scalar components, 2 vector components, and 1 tensor component. Okay, so the 4 scalar components, the first one is simply related to the 0, 0 term of the metric. Now the 0i terms here that are equal to the I0 terms. If I want to split it under irreducible components under rotation, you need to split it in this way, in which, so this is now a sort of a vector, okay, with three components, and you split it in this way, in which you have one scalar, okay, so this you write as the divergence of this scalar, plus one vector which is divergence-less. Okay, so here this vector would have in principle three components, but one you fix with this condition, and the third sort of component of this quantity becomes the scalar. Okay, so from out of H0i, then you get one scalar and you get one divergence-free vector. And now the most difficult part is the space part of this tensor, which is, I remind you, symmetric. Okay, and there to express the irreducible parts under rotation, this is the most general decomposition. Okay, and so you have actually 2 scalars. The first one is simply the trace. Okay, and then the second one is actually a part that is still a scalar but is not connected to the trace of this tensor, and it is this E. Okay, that is extracted with this kind of projector. And so we have here 2 scalars. Then there is one vector, okay, that is a divergence-free vector. So if you take di fi is equal to 0, okay, and it is the decomposition is written in this way. Okay, so that if you take now here di hij, you get actually 0 from here. And then there is the residual part, which is a part which is that is traceless, okay, and transverse, okay, so it is the tensor part hij. Okay, so we have seen here that we can rewrite this metric tensor in all generality by expressing it in terms of these particular quantities that then behave in a given way under rotations, as scalar, as vector, and as tensor. And this is in particular done in this paper, Flanagan and Hughes, that I recommend you to look at. It is also done in the book of Carroll about general relativity, and it is the same thing that one does to define metric perturbation in Friedmann-Lemaitre-Robertson-Walker, okay, so to define cosmological perturbation theory, and is done in the book of Ruth Durer. Though in that case, the background metric is not Minkowski, but it is Friedmann metric. Okay, so now we have then re-expressed this tensor, and now let's see what happens if I apply a coordinate transformation here. Okay, this relation is still valid. And now we also need, for clarity, to decompose our for vector that represents the coordinate transformation as much as before, but into scalar and vector components, okay, for clarity. So there is one scalar component, which is the zero component, and the I component, again, pretty much as done like here, one decompose it with a scalar and a divergence-less vector. And then one needs to calculate, okay, it is not at all trivial, so I'm not doing the calculation here, but you can find it in Flanagan and Hughes, that this provides two scalars, one vector and one tensor gauge invariant variable, okay? So you do analyze how all these quantities transform under this particular coordinate transformation, and out of all the transformations of these quantities, okay, which represent your original tensor, you combine them in order to find quantities that remain invariant when you actually apply this coordinate transformation. And in the end, you are left with these quantities that are, so big phi, okay, that is expressed, so this is a scalar and is expressed with this particular combination, because if you find a way under which phi, b dot, and e double dot transform under coordinate transformation, you see that this particular combination is gauge invariant. Theta is another scalar that takes this form, which is also gauge invariant. And then you find one vector, okay, which is divergence-less, okay, this is a vector component. And then you actually find that your tensor component is automatically gauge invariant, okay? So it is exactly the same as before when you actually try to transform this tensor using this coordinate transformation, because the coordinate transformation is done by one vector that always only has a scalar and vector component and no tensor component, actually you cannot change your tensor. Okay, so the tensor component is automatically gauge invariant. Okay, and now, because these components now are gauge invariant, they are the physical ones. So they represent the physical degrees of freedom of the original metric perturbation here. And how many are they? There are two scalars, there are two vectors, and there are two tensor components, because Hij satisfy the condition of being transverse and traceless, okay? And therefore, in the end, you only have 6 physical degrees of freedom, Okay, mind you, not 2 as we had before, but 6 physical degrees of freedom. Why? Because we have now the entire metric perturbation here. Okay, so this is exactly what happens when you don't restrict to vacuum. Okay, you have these variables that you know they represent physical quantities, and they have in total 6 components. You can also do it by the fact that you start with 16 free function. You get actually 6 constraints, which are, if you sum them, all these constraints here. And then you also subtract 4 constraints, which are from this gauge transformation. And in the end, you get 6 physical degrees of freedom. This is not at all trivial. You need to, if you want to see it, you need to calculate it. Okay, and now we also drop, now it's 11:55. Let me continue just a little bit because I am almost done. We also said that we want to drop the condition of empty space-time, right? The condition of being in vacuum. So up to now, I have acted on the metric the metric perturbation that then is at the left-hand side of Einstein equation. And we have exploited these invariants under rotation, and we have represented this as quantities that are invariant under rotation, and then we found the gauge invariant quantities. Now let's do exactly the same with the tensor that appears on the right-hand side of the Einstein equation, meaning the energy momentum tensor. That is not 0 now, okay, because I have dropped the condition of empty spacetime. So we proceed exactly in the same way, because this is again pretty much as the metric tensor, a 4x4 symmetric tensor is the energy momentum tensor. And so you have T00, of course, is the energy density. T0i, you decompose it in this way. So you have one scalar, this is the 4 velocity, one scalar and one divergence free component. And then in the ij part, of course, you get the pressure, the shear, the heat transfer, no, sorry, that's the heat transfer, the anisotropic pressure, and this and the velocity. That satisfy this quantity. So again, because nothing has changed, you get 4 scalars, 2 vectors, and 1 tensor. And now these are actually gauge invariant automatically. Okay, but you have, so this is not obvious, you need to demonstrate it, okay, but you also have 4 further constraints given by energy momentum conservation, okay, and this is due to this equation, and is okay since we are still in linearized theory. And so you end up pretty much as before with 6 physical degrees of freedom also for the energy momentum tensor, okay? And therefore, in the end, what you need to do is to basically re-express Einstein equations with your gauge invariant variables that are the physical degrees of freedom. Okay, and among these, when you do this, you want to find what is the metric perturbation variable that obeys a wave equation. And again, this is a quite complicated calculation, but what you find in the end is that, so remember what we had? We had 2 scalars for the metric, 2 scalars, one vector, and 1 tensor. So in the end, we have 4 equations for these 4 quantities. They exactly corresponds here to 2 scalar, 1 vector, and 1 tensor, which is what you get out once you impose energy momentum conservation. And so you find this, which is basically Poisson equation. This equation here and these equations here for the vector perturbation. And then you see here that out of these 4 equations for the 4 gauge invariant variables, there is only one equation which is wave-like. Okay, and it is the equation that that express the dynamical behavior of the tensor component. Okay, so you find 3 Poisson-like equations and 1 wave equation, which means that only the transverse traceless metric component is actually radiative. Okay, so it is only this particular gauge invariant component that behaves as a wave. And therefore, it is this particular component that we call the gravitational waves. And now you see we are not any longer in vacuum because the relevant equation is box Hij equal a source. And the part here that is the source is going to be clearly the tensor component of the energy momentum tensor. Okay, so this demonstrates that it is actually possible to express the fact that gravitational waves, so the part of the metric component that obeys a wave equation, have only 2 physical degrees of freedom because Hij, because of this condition that it needs to satisfy, only has 2 degrees of freedom, without having to restrict to vacuum, which is what we had to do in the first part. Okay, so in the end we find this particular equation that is satisfied by gravitational waves. Okay, one can actually do a very nice analogy with the cosmological case, but this I leave as an exercise and then I stop here. Okay, I can take questions.
Okay, thank you very much, Chiara, for this excellent introduction to the theory of gravitational waves.
Thank you.
Time for a few questions. There is a question from online. You can unmute and speak yourself. Pushti?
Good afternoon, ma'am. Am I audible?
Hello?
Yes, ma'am. Am I audible, ma'am?
Yes.
So my question is that when we were studying GR, first we started from the parallel transport. So right now you were talking about gauge invariant variables. So is it necessary to take gauge transformation, or instead of that, parallel transport can be useful to reduce the constraints?
So parallel transport is not used to reduce to reduce constraints, as you said. Okay, so parallel transport is something that yeah you find in the theory, but here it is not of course it's still valid in the linearized theory, but it's not a concern for us, if I understand the question correctly.
Yes, ma'am.
Okay.
Yeah, so I mean, in that case, affine connections were zero in the flat time space-time curvature, and right now,
Wait, it's not zero. The affine connection is not zero. It's just first order in H.
Okay, ma'am.
Okay. So with this particular affine connection, Riemann tensor, etc., you can formulate the theory as you do in GR. You can write the geodesic equation, the geodesic deviation equation. You can define a Lie derivative, a parallel transport, everything you want. It all goes through with the but at linear order in H mu nu.
Okay, ma'am. Got it.
Okay.
Yeah,
Thank you.
I was asking when you did the counting calculation, so that is the 16 components for the perturbation and 6 components for the vector and like another 4 component with the metric, right? So I'm asking that why 16 for the perturb, because it is also like the perturb G mu nu, even in general, should be symmetric, right?
Yes,
so,
yes.
So it should be 10, right? No, not here. I mean the later. I mean not the flat background. after
Yes,
that.
yes, absolutely. But so here you start with 16 because the fact that it is symmetric is into the 6 constraints.
Oh, okay. So that is basically 10 and 4. So I'm asking that when you take the FLRW background, we get another 4 out because that the vector one is, how should I say, divergence free, right? So here also you are splitting the divergence and divergence not free in the previous slide.
Absolutely. Yes. So psi here is divergence free.
So it should be 2, right? I mean, there should be another -4. I mean, 2 vectors, 2 divergence free. So that means 2 and 2, 4 components. So that's what I am missing here, actually. I mean, shouldn't it be, I mean,
So
the vector
also in
components.
cosmology perturbation theory, you get the same. You get 2 scalar gauge invariant quantities, 1 vector gauge invariant quantity, and 1 tensor. You get the same.
I see. Okay, I'll again check later, maybe.
Yeah, check it
So the vector has 2
book.
components, right? I mean, it's basically gradient free vector.
This is 2 components, yes.
Okay.
This has 2 free components because the third one is fixed by the divergence free condition.
Sure.
Am I audible, ma'am? Hello. Hello, am I audible?
Yes, we can hear you. Please speak.
Okay, yeah. Thank you, ma'am, for the lecture. I think my doubt got cleared regarding how it works with the method, but I just wanted to ask that there will be one wave equation, but there will be 3 other Poisson-like equation. So what kind of behavior it will show when the matter is around? That's what I just wanted to ask.
Yeah, so this, it's part of the exercise in the cosmological case. So maybe I let you think about it. But here in the case around Minkowski, you basically find something that is a Poisson-like equation. So these are these are components of the gravitational field that are not dynamical. Okay, that do not behave as waves, but they are variations or perfectly fine and physical variations of the gravitational field, but they are only in space.
Okay, they are not in time. They are not varying with time.
Yeah.
Okay. Yeah. Thank you.
Okay, I do not see any further questions. So thank you very much. Let's speak to the
Okay.
speaker 1 second.
Okay, thank you very much then, and see you tomorrow.
Yeah, see you tomorrow. Thank you.
Bye-bye.